The next few videos will go through something called colligative properties. So this is not anything that we've talked about up until this point. This is specifically how solutes affect solvent properties. So we'll be looking at the solvent, looking at what is dissolved in it, and then figuring out how the properties of that solvent have changed. So it depends on, in general, colligative properties depend on the number of solute particles in solution. So we will have to take this into account in the calculations that we're going to do, and we will be able to ignore the vapor pressure of any solids. This seems like maybe a weird point to bring up here, but one of the properties we will look at is the vapor pressure of the solvent. And if you remember, when we were looking at phase diagrams, that we had a phase boundary line between the solid and the gas. So along that line, you could look at a vapor pressure for a solid. Now, the thing is, those values are really teeny tiny in comparison to the vapor pressure of a liquid. So for all of our calculations, we are going to ignore that vapor pressure. So there are 4 properties we're going to talk about. In this video, I'm just going to list those properties, and then we're going to talk about the specific factor that we put into some of our equations to account for the number of particles in solution. So the 4 affected properties. Well, the first one I already mentioned. It's the solvent vapor pressure. The second and third one we are going to talk about together in the same video, but the boiling point and the freezing point of the solvent are affected by having solute in there. And then the last one is something called osmotic pressure. I'm sure you've heard of osmosis. Osmotic pressure is related to that, and it is greatly affected by the number of particles in solution. So the way that we account for those extra particles is with something called the Van Hoff I factor. And this factor directly communicates the number of particles in solution. Now, you will be able to figure this out without having to do a calculation, but there is an equation that goes with it. So the equation for the Van Hoff I factor is the moles of particles in solution divided by the moles of formula units dissolved. Now that's a lot, but this, like I said, you would be able to figure out on your own. If you imagine something like sodium chloride going into solution, you can get the Van't Hoff I factor, if you dissolve 1 mole of sodium chloride, if you dissolve 1 mole of anything, you can just count how many pieces it breaks up into. So this 1 mole of sodium chloride split up into a sodium plus and a Cl minus. It has an I factor of 2. Now, we could fill this in with the equation. So if we used the equation to do this, the moles of particles in solution, well, I've got 1 Na plus and 1 Cl minus, so that's 2 moles in solution divided by the moles of formula units dissolved. That came from 1 mole of sodium chloride, so 2 divided by 1 is just 2. So this is, in a perfect world, we are going to generally just pretend that we live in a perfect world. So there will be some cases, especially say if your solution is really concentrated, where your I factor is less than you would expect. I will not ask you to predict that. So unless you are given an I factor or you are asked to calculate an I factor based on every other piece of information in the problem, you can assume that things are happening in a perfect world and that everything splits up totally. For things that are non-electrolytes, so non-electrolytes, this just means that it dissolves without breaking up the molecule. So something like sugar is a non-electrolyte because it dissolves, say, in water, but it's still whole sugar molecules once it gets into water. Your I factor is 1. Because you get 1 particle in solution for every 1 formula unit that dissolves. So we do have to include the I factor for all colligative property calculations. You will see it appear in most of the equations that we use. So this is why we're talking about it now. And in the one case where it doesn't show up in the equation, it'll be kind of secretly hidden. And we'll do an example that shows you how the I factor is included in the calculation.